Now, yesterday's session was sort of cramming a quart into a pint pot a bit time-wise, but if I wind up going at 100 miles an hour today, that's more because this happens to be the current subject area that I happen to be rather wildly enthusiastic about. So, without further ado, bit of an introduction to serverless architectures. I hope I'm not going to be stealing Martin's thunder on this. And then some thoughts about actually looking at serverless architectures and indeed AWS architectures in general from a threat model perspective, thinking about all the bad things that could go on if I was to stick a notional black hat on. What nastiness could I cause to happen? And then how would I stop myself doing it if I switch back to the white hat? Although I don't do the whole Ronnie Barker hat sketch thing. Little bit of a look at IAM and permissions in the context of serverless, and then some things I've been working on with our friends at Alert Logic about how to go about wrapping Lambda functions to do sanity checking front and back of what inputs they're getting and what outputs they're generating. So essentially how to black box Lambda functions in situ. It turned out that what we came up with for doing the back end of the black box was actually more generalizable using API Gateway and Lambda again, where API Gateway is probably my new favorite service. And then actually how that can be generalized across APIs as a whole from an AWS perspective to add extra layers of protection to all the AWS APIs. And we should have time today, a little bit of a surprise on the end. Unless you've actually seen this session at reInvent, the video is up as SAC 310 on YouTube, so I won't spoil the surprise in case you haven't. So there was a fairly big hoo-ha about 2 years ago when we launched Lambda, and serverless has been the very much the hot topic of the moment since. However, serverless is a long way from new. I mean, when you look at it, S3 is actually a serverless service from a customer perspective. You don't get to interact with servers. You don't need to determine what the sizing of your service is. You just take your data, determine how it has to be protected, whether that be through access controls or access controls in your bucket policy or encryption, or as we recommend, both. And you just drop it in S3 and you let S3 get on with it. So all you need to worry about is the functionality the service offers rather than how you actually go about managing and maintaining it. That's our job. Now, on the serverless side, up until reInvent, you could normally characterize a serverless service in terms of this little list here of what it actually does, what they actually do. I've updated this table here since reInvent. And as famously, we now say that we have 70-something, probably getting on for 80 now, services. If we take a look at this, we've got 2, 4, 6, 8, 10, 12, 14, 16, 32, 63-ish. Considerably more than half, put it that way, of the services AWS offers are actually serverless by my rule of thumb, which is that you don't have to go sizing things from the point of view of the execution environment that you're using. Lambda is a little bit of an exception for that, but Lambda is a little bit of an exception for a lot of things in a good way, as we'll be getting onto. So here's an example serverless architecture that I blatantly ripped out of someone else's previous year's reInvent deck. And common things that you see in serverless architectures. First of all, you wind up having remote environments calling APIs. The whole thing tends to be API driven. Also, you often get API integration with external services like Twilio and Slack, as you've got here. And then from your API gateway, you wind up fanning out into a whole number of Lambda functions based on what the RESTful calls are actually doing in order to go calling various backends to do stuff, and using S3 for your logging, static hosting, various other repositories, and visualizing stuff in Kibana. This is a very common way that things hang together in a serverless world. So looking at the world through security-tinted glasses as I do, what can go wrong? So everything starts with a threat model. Pretty much everything in my world starts with a threat model, to be honest. What can we actually do from a badness perspective? We do a lot of threat modeling at AWS. We use Stride, we use Dread, we use a whole bunch of others. But the thing about threat and risk is it's something that the human brain is fundamentally bad at, as Bruce Schneier and other Illuminati have written at great length. I've actually, I think I read a few months ago, and which is actually a nice read if you're into this kind of thing, is there's an MSc thesis from a chap named Dan Ionita from the University of Twente, where he kind of has a gazetteer of it comes out as being 27 different threat risk models, some of which I knew about anyway. There were a couple in there I didn't, but I also know about a couple that he didn't list either. I've even invented one back when. So ultimately what you need to look at is who can do bad stuff, what means they have of doing that bad stuff, and the consequences of the badness when it happens. And there, of course, this is where you then wind up standing up mitigations to stop it happening in the first place. So consider an AWS API. So if things have input, they've got attack vectors. These tend to split into in and out of band. But there's also the matter of just using a service as a propagation vector rather than necessarily compromising it itself. Imagine, if you will, taking some piece of malware, it needs to be a fairly small piece of malware for this example, but let's consider that later. Drop it into SQS as a message, in the understanding that at some point an EC2 instance with some vulnerability is going to pluck that message off the SQS queue, consume it, get compromised. No fault in SQS in this context. It has done its job by propagating the message from point A to point B with appropriate queuing and control and so forth. It's just that the actual consuming point has the issue. But can we do things with SQS to deal with that? More later. So obviously for the actual things that you could go putting in that kind of payload, start with the OWASP plot 10. So let's have a look at so that's in-band attacks essentially for a service. Now let's look at out-of-band attacks against the actual API. When we actually built our SIG-v4 API call mechanism, we did a lot of thinking about it from the point of view of integrity and non-repudiation, confidentiality, plus of course the scaling of the API endpoints themselves. They all auto-scale, and we monitor and throttle the traffic to them, gives us our availability. So with a SIG-v4 call, you're framing your REST query or query-based URL, adding a timestamp, adding your AWS access key, whether statically generated or better still ephemeral, out of our secure token service. You're doing a SHA-256 HMAC over that with your secret access key, and you're sending it into us. We then verify that the call is appropriately constructed. We dismantle it as needs be and get it parsed by the respective services parser once it's been checked against IAM to determine that you've got the permissions to do what you're trying to, and it all hangs together pretty well. We're using S2N now, which is our own implementation of TLS 1.2 to do the crypto on this. It looks pretty well sorted to my eye anyway. But if you look at what those payloads can constitute in your RESTful calls or your API query-based calls, you can actually put a lot in one of these calls and the payload that goes along with it. So I've just picked some example payload sizes by service here, and there is leeway here to potentially get some interesting and bad payloads in band into API calls. This is interesting. So what can we do about it? First things first, IAM is a fairly sharp instrument for this. If you want to use it bluntly, the obvious thing you do is deny access to your APIs to anyone except the people you really want to have access to them. And this is something that IAM's really good at. We recommend, as is worth saying here, that anything that is doing interesting privileged operations be assigned to a role rather than a user. This means that you're authenticating to make that call using ephemeral keys via our STS service, and this means that there is less incentive for engineers who should probably know better to go wiring static API keys into their code and then posting their code up to GitHub and then finding, as we all know from the press, that their AWS account is suddenly mining Bitcoin. So using STS and roles de-risks that particular kind of threat vector effectively, so that's an obvious thing to do to begin with. Also, a thing I'll be getting onto in a slightly different way a bit later is if you actually start doing things cross-account, using cross-account IAM roles, for certain services that support this, you can actually bend the means of access to those services and their APIs and restricting permissions to a level where you effectively get mandatory access control. And those of you who are in yesterday's session will know that mandatory access control is something I have a fixation with that borders on the unhealthy. But more on that as well shortly. So mostly you can constrain API calls by source IP in your IAM policy. If you have if you're using the kind of API that itself goes making API calls, that is a bit more of an issue, and there are details as to which kinds of calls those are and means of addressing the problem in the architecture I'll be presenting. In terms of the means of making API calls from AWS environments to the API, we publish our IP ranges, which are themselves pretty large, but you can scope them down by region to ensure that one region is only able to call itself. And we'll be using that later with our wrapper functions. And of course, if you start by default by assigning things a little bit permissive, you can very easily audit when specific permissions were used. So after an API or an environment has been active for a few months, if there's calls that haven't been used, you can chat to appropriate people and see if you can gracefully drop them. So this is an interesting bit of research currently ongoing with friends at Alert Logic. Though I have also, just this morning, got wind that there is a stealth company, a startup currently in stealth mode, who I hope to be seeing next week, that are also doing something that might kind of mesh with this nicely, but I'm afraid I can't talk any more about this yet. So if we want to go securing our serverless architectures, Lambda's a nice place to start as a test case. Reason being, Lambda actually executes your code. Anything that you are able to write in Python or Node.js or Java, or any languages that can be called from those, a common thing to do is actually use a Node.js shim, which is doing the rounds on the internet, to go calling pre-compiled functions that you've built in any other language. I've even seen people write Lambda functions in C before now. But as we all know, you can write insecure code in any language. It's supposed to be impossible, but I've even once seen insecure code written in Ada. They had insufficient rigor on the traps that on the trap handlers that were supposed to catch errors. So there is no accounting for what engineers can get up to if they want to. Obviously, when it comes to security, the first thing you need to do is ensure you're sanitizing your input. Not everyone does. We've all seen the well-known XKCD cartoon where little Bobby Tables winds up, by virtue of his name, deleting the school's database system. This is very much the same idea here for license plate for automatic number plate recognition. Not everyone sanitizes their input, despite it being OWASP threat number 1 in the top 10. So if we consider what our Lambda function would normally do, we've got our function here that is being triggered by an event, let's say an object being written to an S3 bucket. It runs in an IAM role. Let's say it has a permission, whatever that permission may be, to go making a function call against a generic API endpoint for some AWS service. Let's now put some wrapping around this. So we're going to make ourselves a little front-end service here involving another Lambda function and some extra magic box. And we're going to filter our API call going to our API endpoint by having a new backend on here. So let's look at our front end to start. So instead of having our main Lambda function here get triggered by an object getting written here, we instead trigger a wrapper function. That wrapper function goes and passes the data from the trigger and its context to some analyzing box, which needs to have the same permissions as our main Lambda function would have here in order to read the data that has been written and therefore triggered the event. It can then go doing some analysis on that data to determine if there is any badness in there for some value of badness that we choose to define. If there is considered by the function to be no badness, it can go invoking our main function as though it had been called by the event from our bucket. It can pass that context along with it, and then our main function can just execute as it ordinarily would. So things that we need to look at and what we can potentially do. We can either do this checking synchronously or asynchronously. We may want to do it asynchronously if the performance of our Lambda function is critical. Normally, we would choose to do it synchronously so that our main Lambda function only gets called after the payload has been scanned for potential badness. Otherwise, we would wind up having an execution path, potentially doing things with badness that we would need to trap and undo. And, well, prevention is always better than cure, put it that way. We could do things around machine learning to determine what kind of usage patterns we were seeing of our Lambda function. There may be interesting things mineable from that about the behavior of potential threat actors. Obviously, we can use traditional techniques to go looking for malware in our payloads, and we can also go looking for the same kinds of threats that our WAF does in terms of doing things like cross-site scripting and SQL injection. A friend of mine, when I showed him this, he actually referred to it as being WAF for the API. So people, when they were talking to Alert Logic about this, were saying SQL injection, 2017, yeah, sort of banging rocks, trying to make fire. Turns out from Alert Logic's stats, doing all their threat intelligence and modeling that they do, that back in 2016, they were seeing an awful lot of SQL injections still. About 39% of the malware they were looking at was of this nature. So it's still out there. It still needs stopping. There are still people not reading the OWASP top 10. Either that or bad guys are still banging rocks trying to make fire while the defenders of good infrastructures are sitting there flicking a Zippo or something.
Is that attempts or attacks?
That is attacks. So let us take a look at an example API call that Alert Logic crafted up. So if you actually decompose an AWS API call, extract it out of the SIG-v4 framework, you can wind up getting something like this. This all looks reasonably fine, although this is all rather opaque. If you take that and you base64 decode it, oops, we got an SQL injection. So what can we actually do to go looking for stuff like this. I mean, it doesn't necessarily have all the 1 = 0 stuff that you typically get in SQL injection attacks. So what can we actually do here to go looking at this? And Alert Logic went and borrowed bits out of their analysis engine and built a little scratch box here. This is a lab environment that they put together, where they're essentially using this architectural pattern for looking for SQL injection in people trying to go logging into a little website and also get hold of Cognito creds. So the actual wrapper function that they use is just this little bit of Python. It's not hugely complicated. It just picks a handler up, throws it off to the analyzer, sees if what it gets back is a thumbs up or a thumbs down, and goes calling our main function if the thumbs up comes back. Not a complicated piece of code. And if they wind up using a proper set of login credentials, they wind up getting in. If they wind up using, if they wind up trying to do something mischievous here, then they wind up getting thrown out. And yeah, engineer can't spell. Now, that's the front end in terms of wrapping our Lambda function. Let's look at what we can do with the back. So here we are with our Lambda function executing in its role, making an API call to an API endpoint. What fun can we have here? How can we actually do some useful things? What we want to actually do is use our API gateway as a proxy. So we want to make our Lambda function think that our API gateway is actually our API endpoint. We can get logs out of it, which it's something that is a fact that we don't talk about a great deal, is that not every AWS service intrinsically has CloudTrail integration. All the ones that are released to production do. It's a thing that comes along very quickly if it's a service that's in preview as an enhancement before it goes to production. But when we've got really newly released services, not everything can do CloudTrail straight out of the box. So one of the things that you can do with API Gateway is actually get decent logging out of it. So if you're using some of our brand new services that may not have CloudTrail integration, doing this is not a bad thing to do anyway. API Gateway supports SIG-v4 straight out the box. So we immediately have the ability to make our API Gateway pretend to be an API endpoint. But now how do we convince our Lambda function, without getting too messy modifying our code, to use this instead of the real endpoint? Inside the SDK for Java and Python, at least, there is a file, and you'll see the URL for it later, that actually, its sole purpose is to make mappings between the names that the endpoints have for specific services that are the names you call in your API calls, and their fully qualified DNS domain names. That's all that this file does. So how about you take this file in the SDK that underpins your Lambda environment and you tweak it. So instead of pointing to the real endpoint, it points to the gateway that you've stood up. You can do that. So obviously, you need to make your Lambda function a little bit two-stage in that it needs to ensure, first of all, that that hack's in place and you're now talking to your gateways rather than the real ones, rather than the real endpoints. But then you just check that and invoke your real function. So we've been talking about doing this for Lambda functions calling API gateways. How about anything calling API gateways and API endpoints? You can do that. And here's a little architecture. So if we've got our client, whatever it may be, we hack its SDK. These are the file names as to where you'll find that mapping file in boto, the Python SDK, and also in the Java SDK. I looked through the JavaScript SDK, and I didn't actually find a file quite like this. It's more distributed across the different API modules for the individual services, so there would be a bit more hacking to do. But it's there, it can be done. The other thing to bear in mind is that when you actually go standing up API gateways, they intrinsically wind up getting themselves an HTTPS cert key pair when you stand them up. Those are themselves also rooted in AmazonAWS.com. So this means that unless you've actually been using this SDK already, pointing to the real API endpoint, you shouldn't have any trouble with DNS issues or certificate pinning or any of the appropriate security things that are stood up to protect the endpoint. So set your API gateway up to use SIG-v4. Have it decompose your API call. In all honesty, while you can do a lot of subtle and sophisticated things in API gateway, I find that unless you're actually building things in a Swagger file and importing that, it can be easy to tie yourself in a bit of a knot with it. So I would actually suggest that unless you want to go building your API in Swagger to begin with, this is just the way my brain works. Then it's easiest to do as little modification of your calls in your API gateway as possible, and pass things over HTTPS, which is standard out of the box, to your Lambda function. So your Lambda function is running in a cross-account role. So this little wrapper around here is a separate AWS account. And there are reasons why we do this, which again get covered in the cross-account and mandatory access control presentation. So we have an interesting split horizon here, because we've got our user out here who's making a call into our gateway here and is known by this account here, but the call across to the account here that has the real resources in is actually being made by our Lambda function, not by our user. So we have a split horizon ownership handoff in our Lambda function, or we can if we want to. And you can do interesting things with this. But let's not get ahead of ourselves. We have our cross-account role. We can make that typically be most permissions associated with the service. We go having our Lambda function make a real API call to the real API endpoint, and then things proceed as normal. So things you can do with this. So we've got a general architecture. Let's actually see what we can do to put it to use. Now, I like config rules. I spoke about them a little bit yesterday. The idea is that while IAM can give you the same kinds of permission constraints as Linux RBAC can, there are some things you might want to enforce that IAM can't intrinsically enforce. So, for example, while IAM can constrain who can, in whatever circumstances, go creating an EBS volume in whatever environment, they can't necessarily, IAM can't actually insist that EBS volume is encrypted using KMS. So if you have a policy that requires that your EBS volumes be encrypted by KMS, you'd have to have a config rules element, a Lambda function in config rules, that would, when the event happens of creating your EBS volume, say that EBS volume isn't encrypted. I'm either going to delete it, or I'm going to fire off an SNS topic to appeal to a higher authority to deal with the problem. In this case, you could actually decompose the API call, which is a query-based URL rather than a strictly RESTful API. Well, it is strictly RESTful, but it puts a lot of stuff in one URL call. You could use some URL parse to take that API call apart, detect that you're trying to create an EBS volume, see that there is no key argument in there, therefore the volume isn't encrypted, and go, bzz, that's against policy, dude, go away. All of a sudden, your volume hasn't been created. Admittedly, you have to write code for this, which can get complicated if you've got a lot of API calls that you want to filter on. In extremis, it could turn into something as complicated as an SE Linux profile. And I'm trying to think about how it could sensibly grow while still remaining tractable, because of course we have an awful lot of API calls at AWS, especially when you start thinking of the permutations and combinations of arguments that can be applied to them. So this is something I'm still thinking about. For those services, another example, so for those services that you can't intrinsically do source IP address filtering on at the moment, this is a way of doing it, because you're filtering here on this source IP address here. This out here only needs to know that you're coming from an AWS IP address, and in fact you don't actually need to filter on the IP address back here, because only things with this role can go making that API call in the first place once you've set them up appropriately here. So you wind up actually using the role, which our guide out there doesn't have, in order to act as our surrogate of a source IP filter. And so you kind of have a transitive trust between the resource area, the resource account here, and the Lambda function here. Again, it can be made to work. SQS is something that it's one of the first services we introduced, actually. Gets a lot of use, but I do sometimes wind up talking to customers who have a conservative view of security, often in highly regulated or controlled industries, and they think, wouldn't it be nice if SQS was encrypted? This is a way to do it automatically. So you could have your Lambda function have permission to encrypt your payload with a KMS key, only then does it actually wind up going into SQS, and you could have some other thing consuming the queue, like an EC2 instance, have a decrypt grant on the same key. So out here, you just wind up making an SQS call. This picks up that it's an SQS call, encrypts it, proxies it transparently to you. And this is one a friend of mine in Germany came up with. I've worked with customers who like to have workflow systems. Originally, the customer I'm particularly thinking of, they wanted to do this because there's a certain kind of software engineer whose approach to performance is to run everything on a C48X large. They had some of these guys, and they wanted to ensure, even though they're a global company, that their engineers could only fire up certain instance types if they had management approval. So they spent a very large amount of time, effort, and money with a system integrator to produce something that was effectively a cloud gateway standalone on their own premise that would go filtering API calls and engage a workflow whenever it saw something like a particular instance type being requested. Again, you can have, this is only the beginnings of a system. It's not a full integration, but if you had some workflow engine out here whereby management could pre-approve an engineer to fire up a particular instance type, they could put some kind of signed message into a queue giving that approval, and our Lambda function could check for the existence of such a message and consume it, and only at that point allow the API call to succeed. Otherwise, hello 403 again. So it's potentially a touch point whereby workflow systems could be integrated into an API call mechanism. And the final case, as previously mentioned, is rather than just using, just wrapping Lambda functions and building WAF for the Lambda API, you could actually generalize this into being WAF for all the AWS APIs, scanning for badness in whatever form you think badness may take. This is something, bearing in mind that Cyber Essentials requires anti-malware as one of the 5 constraints it imposes. This could be a way of doing it at an API level. In terms of what you actually wind up doing with your Lambda function and how you trigger it, these are all the services that currently have the means of calling Lambda functions. So the scope of what you can do is pretty large. It's a case of use your imagination as to what you can actually do here. So just to wrap this piece of the presentation up, we've got an interesting new tool for our toolbox in terms of being able to pre-filter API calls and wrap Lambda functions. Obviously, IAM is your first port of call for limiting who can make API calls in the first place and the contexts in which they can. The API endpoints, we've got them reasonably sorted. We look after them very carefully. And you have the means of using Lambda in API call flow to do things like split horizon API call ownership changes and generally proxying our API endpoints when you stick an API gateway in front of it. I'm interested to know other ideas you have for applying this little architectural pattern, and very interested to engage in discussion as time passes if you look to use this. And not Steve Jobs, but I happen to like this approach to doing these things. I have a fixation with mandatory access control. So when you look at the AWS API, it is classic Unix discretionary access control. You've got this all-powerful entity called root that can do everything and completely blast through policy. This is getting addressed to a reasonable degree, starting with AWS organizations, which we announced at reInvent. This is something I'm looking to build into this piece of work. But for a while, in terms of an in-account mandatory access control environment, we've had Glacier Vault Lock. So what can we actually do to take root away? We can't actually get rid of it completely without a lot of work from IAM engineering, but what if we were actually able to completely conceal the nature of an AWS account from its users? Well, using the architecture we've just come up with, we pretty much can. Plus, there's an extra bit on the back end. My pal Bertram in Germany came up with this idea for actually filtering logs in order to meet compliance requirements of German data protection law. The idea being here that if you have your CloudTrail logs, for example, that go landing in an S3 bucket, your CloudTrail logs contain a bunch of personally identifiable information, such as the details of the user that made the call, plus also in German law, the tuple of a source IP address and a timestamp is also considered to be personally identifiable information. Yes, I know. So Bertram decided to write himself a Lambda function whereby when a lump of CloudTrail record lands in a bucket, it gets picked up, has the PII in the form of the username and the IP address and timestamp redacted, starred out, and then stores it in another bucket. The reason why you do this in Germany is you are allowed to retain the redacted version for as long as you like in terms of your regular long-lived records. This, with the PII in, you have to get rid of after a period that isn't, to my understanding, well-defined in law. I'm not a lawyer, by the way, much less an international lawyer with knowledge of German law. But you have to effectively throw this away. So Bertram just sets an S3 lifecycle policy that deletes the contents of this bucket if an object happens to be older than 31 days. So if we consider that as our back end, we can use this model for redacting more than just CloudTrail logs. We can redact all the logs associated with an AWS account. In fact, when I'm talking about redacting here, I'm not talking about redacting the PII in the logs, I'm talking about redacting the account ID and potentially replacing it with something else, because we want to see about hiding our account. And it turns out that if we nest our API proxies, as we showed earlier, we can actually do that and get this big complicated diagram. So what we're doing is we're using our split horizon. So our guy out here goes making his API call, goes to this Lambda function. He's making his API call against the account ID of this account. This Lambda function is rewriting that API call and making it against the account ID of this account. So when the response comes back, the Lambda function needs to rewrite it before sending it back out through the API gateway to our customer. Now, if you do this in a two-stage fashion, and you also apply Bertram's function here on the back end, then only people who have the ability to look inside this red oval can determine what the true account ID of the account holding our resources here is. Because you're rewriting here to this account that is the only thing that has knowledge of this account ID. You're rewriting here, which has knowledge of the real account ID, to this account that doesn't. This is where your audit and logging team would go looking. And this turns out to be completely hidden. So while we have the ability currently for customers to put root beyond use by assigning an MFA token and then destroying the token, normally use a soft token rather than a hard token for this, we can now actually completely conceal an account ID. So, okay, root still exists, but root on what account? Nobody outside this circle knows. Food for thought, I hope. So, same thing here in text, so that the presentation stands alone without me waffling over it. But because we're able to conceal the account and conceal all the policies on it, and essentially take away root even from the ability to go making calls to the support line in terms of, so what's the account ID, sir? I don't know. Then this again gives us mandatory access control. Now, there was an issue I came up with where an EC2 instance inside that concealed account can still go determining what its account ID is by making calls to the EC2 metadata service. But if you actually if you actually limit the EC2 instances that can be stood up to being instances of SE Linux that have a policy on them under mandatory access control that uses the host-based firewall to block access to the metadata service, that closes that door. And I haven't yet thought of another way around it. So this is all research in progress, but I wanted to give you a little look at it in advance. And that's me.
Yeah, I have one question. I worked in past company. I set up everything AWS. I have the root account. I left the company, but still I can access everything of the system. If no, so my saying, if it is not AWS, if it is on premises, I cannot access other systems. But AWS, I still can access everything of the past company.
You might be surprised. I wound up working in escalation back when I was at Sun Microsystems, where it actually wound up being a criminal case because the person who retained access to root, since the company hadn't gone rotating the credentials, they wound up holding them to ransom. But it's a thing that a surprising number of people still, when someone with significant access permissions leaves a company, a surprising number of organizations, even on-premise, neglect to rotate their credentials. So credential rotation in the event of a privileged person leaving is something that should be done no matter whether you're on-prem or in AWS, and it can be done in either environment. People just need to be on top of their policies and procedures.
No, maybe I'll take another. So I worked in 3 organizations. 2 of them use Azure. 1 I created AWS. So none of them have closed my account for this cloud, but I can't access their on-premises infrastructure. I'm not sure because that is not integrated with their Active Directory or something like that. Because let's say my email account or anything, it is linked with Active Directory. So they will close, I can't access anything. But cloud is still, I can access all 3 companies.
I would suggest in that case, you be a good citizen and tell them that they have forgotten to extend the scope of their policies and controls to include their AWS environment.
Okay. My only concern is like people don't, I mean, the only thing I can see, like there are a lot of accounts, a lot of things, like you have email, you have SharePoint, you have AWS. So generally there are different teams who manage. Yeah. So that is the main point of security. Like maybe because in wherever I work, it's not centralized. Like this person have access to 10 systems. So I found the main security point is first place is there. Like
yeah, this is something that my friends at Alert Logic often talk about, in that they see a lot of organizations who are on top of their on-premise security from the point of view of firewalls and anti-malware and data loss prevention and so forth. And they seem to think that a cloud environment magically gives them all this capability, and it doesn't. Even though we get appropriate external certifications on the services that we make available to our customers, you still need to run and manage your cloud environment in an appropriate and diligent way. And you can build wildly non-compliant architectures out of compliant parts in a cloud environment just as you can on-premise. So it sounds like the companies in question need to, it sounds like they have a blind spot, and Alert Logic, while I'm taking words out their mouths a little bit, they see this not infrequently. Sounds like they have a bit of a blind spot about their cloud environments. So, as I said, I would suggest you take some citizenship, earn your citizenship points and tell them that they need to extend their scope.
So last thing. Like everywhere, like recently, like there's a 90 days or 1 week, 1 month password change policy. Is it not like AWS can also implement that by default, that you need to change your default password after certain? It is already there, but I have not put like after 60 days it will expire.
You can set that up in IAM dead easy, but not for root. It doesn't apply to root. That's the thing. But you can set it up in IAM dead easy. We don't set it up by default because it's not our place to tell our customers what their policy is.
It's interesting on that specifically. There was actually some guidance from CSG about requiring password changes, and it's an interesting, I'm not saying I agree with the guidance, but it is an interesting thought piece around forcing people to change their passwords every 90 days, or 60 days. How many of us use the same password basically? 6, 7, 8. Or, you know, you're changing one character somewhere, and actually the CSG guidance delves into that somewhat, talking about forcing people to change. So really us taking a position in terms of what your best practice should be, you know, that's your decision. So yeah, the tool is there.
We do work closely with organizations like the Center for Internet Security to come up with recommended baselines for securing AWS accounts, but it's not something we do by default. Thank you. As we take a Unix approach to security, as with all other things, by trusting our customers to have better knowledge of their business than we do.